Welcome, listener, to another deep dive. Have you ever stood at the edge of the programming world? Maybe. Dreamt of building your own applications, but felt like you needed a Rosetta Stone just to understand the entry requirements.
Or perhaps you're already familiar with code, but are looking for, a rapid, really hyper-focused update on one of the most foundational and enduring languages out there.
Exactly. That's precisely why we're here today.
Yeah, our mission is to embark on a deep dive into the absolute essentials of Java programming.
Right.
We're talking about taking you from square one, like how to set up your entire coding environment, to understanding the very heartbeat of how your Java code comes to life and executes, all the way to building a genuinely practical application. Think of it as your express lane to grasping Java's core principles, distilled from some really great expert guidance.
And guiding us through this incredibly rich material is, well, a true veteran of software engineering. This instructor has decades of experience and has, astonishingly, taught millions how to code.
Millions. That's quite something.
And their promise, to make Java super simple and truly accessible. So if you're ready to sort of bypass the overwhelming noise and jump straight into powerful, practical Java, you're in the right place.
Let's get started.
Okay, let's really unpack this journey then. The expert guide whose insights we're drawing from today is Mosh. Now, he's a software engineer with, over 2 decades of hands-on experience, like in the trenches building real stuff.
Exactly. And what's truly remarkable is his reach. He's personally taught more than 3 million people to code. Think about that. Many of them have gone on to become professional software engineers.
That's not just teaching. That's like empowering a whole generation of developers. It's huge.
It really is. And what's particularly compelling about his teaching philosophy and why it resonates so well with our approach here is that he designs his courses for absolutely anyone.
Right. No prerequisites needed.
Pretty much. Doesn't matter if you're a high school student or, embarking on a mid-career change. Age, prior experience, they're kind of non-factors. His core promise, and it's a powerful one, is to make Java super simple.
Super simple. I like that.
And to quite literally hold your hand through every single step. By the end of his training, you're not just expected to understand Java theoretically.
No.
You're meant to possess a solid foundation.
Yeah.
And the actual ability to write good code like a professional developer. It's really about empowering you, the listener, with tangible, actionable skills.
That's a fantastic goal to set. But okay, before we can write even one line of code, we need the right tools, don't we? It's like you wouldn't try building a house without a hammer or saw.
We really wouldn't.
So what's the very first piece of software we need to get our hands on? And can you maybe demystify what it actually is?
Right, you've hit on the critical first step. The foundational tool you absolutely need is the Java Development Kit, or JDK for short.
JDK.
Now, this isn't just the Java language itself sitting there. Think of it more like Java's complete integrated workshop.
Okay, a workshop. I like that analogy.
Yeah, it's an entire software development environment purpose-built for creating, testing, and running Java applications. It's a comprehensive toolkit, really, that sets the stage for everything else you'll do.
A workshop. So if it's a workshop, what are the core tools, the key components we'd find inside this JDK that make it so essential for developers?
Well, within the JDK, you'll find several critical pieces. First, and this is essential, there's the compiler.
The compiler.
That's the translator. It takes the human-readable Java code, you write those Java files, and transforms it into a format the machine can understand, called Java bytecode. Without it, your computer just wouldn't get your instructions.
Makes sense.
Then you have extensive reusable code libraries. These are just vast collections of pre-written, highly optimized code that solve common problems. They save developers huge amounts of time.
Like pre-built components.
Exactly. Think of them as prefabricated walls or plumbing for your house. You don't have to build everything from scratch. And crucially, it also includes the Java Runtime Environment, or JRE.
JRE, okay. We'll probably touch on that more.
We will.
Yeah.
And beyond these, the JDK packs, well, a bunch of other stuff, utilities for debugging, optimizing performance, managing projects, basically everything a developer needs in one place.
That sounds like quite a lot packed into one download. So for someone just starting out, or even someone just doing a quick refresh, how do we actually go about getting this JDK? What's the practical installation process like? Is it complicated?
Not really. It's quite direct. It's designed to get you up and running without too many hurdles. You basically start by searching online for JDK download.
Simple enough.
The official source, where Java is maintained, is oracle.com. Once you're there, you'll navigate to the Java SE, that's Standard Edition section.
SE, Standard Edition.
Yeah, that's the version for general purpose applications, exactly what we're focused on. You'll need to accept a standard license agreement, just a click through, and then download the installer for your specific operating system, like a .dmg file for Mac and .exe for Windows.
Or .tar.gz for Linux, maybe?
Right. And Mosh emphasizes that the installation wizard itself is super easy. It practically holds your hand, typically just a next, finish kind of experience.
Okay, good. So once the JDK is installed, we have the core workshop ready to translate our code. But to actually write that code, to craft the instructions, we need a dedicated workspace. Yeah. What are the common tools for that, and which one comes recommended for this learning path?
You're absolutely right. Choosing your code editor, or more specifically an integrated development environment, an IDE, is like picking your programming workbench.
Your workbench, right.
This is where you'll spend most of your time. Typing code, organizing files, debugging, running your programs. Now, there are several popular, really robust choices out there, like NetBeans and Eclipse. You might have heard of them.
I have, yeah.
But the tool, highly recommended by Mosh in his course, and honestly widely favored by professional Java developers across the industry, is IntelliJ IDEA.
IntelliJ IDEA. Okay, yeah, I've definitely heard that name come up a lot in developer circles. But, as someone just dipping my toes in, or maybe someone on a budget, is this going to cost me an arm and a leg?
Not at all. And this is a really crucial point that makes it so accessible for learners. Mosh specifically endorses the Community Edition of IntelliJ IDEA.
Community Edition.
And the best part, it's absolutely free.
Fantastic.
Yeah, he gives strong assurance that this free version is more than enough for anyone looking to learn the Java fundamentals and build solid applications. And the installation for IntelliJ is also remarkably simple. Like on a Mac, it's often just dragging the icon into your applications folder. Windows has a simple wizard. It's designed for minimal fuss.
Okay, so we've walked through setting up the JDK, choosing IntelliJ. It feels like a bit of groundwork before we even write Hello World. For a new learner, why does all this setup actually matter so much? What's the real payoff for doing this foundational stuff first?
Well, this initial setup isn't just, bureaucratic busy work. It's your virtual sandbox. Skipping it is like trying to learn painting by just reading about colors.
Right, you need the paint.
Exactly. You need to get your hands dirty, mix the paints, put brush to canvas. This setup lets you immediately move from abstract theory to practical, hands-on application. It's where those lines of code actually do something, creating that crucial aha moment right from the start. For you, the learner, it's the gateway. It lets you experiment, get immediate feedback, and truly solidify your understanding.
Makes sense. With our virtual workbench set up and tools ready, let's finally talk about the actual anatomy of a Java program. What are the fundamental building blocks we need to grasp? Mosh really starts with functions, or as they're more precisely called in Java, methods. Can you explain what a function or method fundamentally is?
Right. At its heart, a function or method, as we should probably call it in Java, is simply a block of code that performs a specific task.
Okay, a block of code, specific task.
Yeah, think of it as a specialized mini program within your larger program. It's designed to do one job, do it well, and that makes your code modular and reusable. Mosh uses a fantastic analogy, your TV remote.
Ah, okay.
Every single button on that remote, power, volume up, channel change, performs a specific isolated task. That's exactly what a method does in programming. It's a self-contained unit of action.
That's a perfect analogy, really visualizes it. So building on that, what are some concrete real-world examples of tasks these methods might handle inside a bigger application?
Sure. The examples Mosh gives really illustrate their utility. You might have a method specifically for sending emails to people, right? All the logic for connecting to the server, formatting the message, it's all bundled up in there. Or maybe a function for converting someone's weight from pounds to kilograms. It takes pounds in, gives kilograms back. Simple. Another common one is validating user input, making sure what a user types into a form is, valid before your program tries to use it. Each one is a distinct, reusable chunk of code.
Okay, so we get what they do, but how do we actually write them out in Java? What's the basic syntax, the structure for defining one of these methods?
When you define a method in Java, you follow a very specific structure. You start by declaring its return type.
Return type, what it gives back.
Exactly. It tells Java what kind of value, if any, the method will give back when it's done. If it doesn't return anything, you use the special keyword void.
Void for nothing.
Right. It returns a whole number, you'd use int, and so on. After the return type, you give it a proper descriptive name, something that clearly says what it does, like send email. Then comes a pair of parentheses. These
So
are
for parameters.
parameters. Okay. They're basically placeholders for values you pass into the method. For send email, parameters might be the recipient's address, the subject, the message body. Mosh notes will dig deeper into parameters later. And finally, you have a pair of curly braces. The actual Java code that performs the method's task lives inside these braces.
And Mosh points out a subtle but important detail about placing those curly braces in Java. What's the convention there?
Yeah, it's a small stylistic thing, but it matters for consistency. In Java, the convention is that the left curly brace typically goes on the same line as the method definition itself.
Ah, okay, not on the next line like in some other languages.
Exactly. Unlike, say, C#, where you often see it on a new line, sticking to these conventions just helps make code look familiar and readable to other Java devs.
Now, every Java program needs a starting point, like a main entrance. There's a special method for that, isn't there?
Absolutely. Every single runnable Java program, no matter how simple or complex, has to have at least one method, and that method is universally known as the main method.
The main method.
It's the program's entry point. What that means practically is, when you run a Java program, the main method is the very first piece of code the Java system calls and starts executing. Without a main method, your program just wouldn't know where to begin.
So methods are individual actions. But Mosh really emphasizes that in Java, these methods don't just float around. They should always belong to a class. This sounds fundamental. What exactly is a class then, and how does it help organize our code?
A class is essentially a blueprint or a template for creating objects later on. But more fundamentally for organization, a class acts as a container for one or more related functions or methods.
Container.
Yeah, it's how we group methods that logically belong together. It helps structure code into manageable, understandable units. Mosh's supermarket analogy is great here.
Great, the sections in the supermarket.
Exactly. Just like a supermarket organizes products into sections, vegetables, fruits, cleaning stuff, a class contains related functions. It stops you having just a chaotic jumble of methods everywhere. And it's a strict rule in Java. Every program needs at least one class that contains the main function. Often, that class is just called main.
That analogy makes it super clear. And syntactically, how do we define one of these class containers?
It's pretty straightforward. You start with the class keyword, then a proper descriptive name for your class, something that indicates its purpose, like mortgage calculator or employee record. Then, just like methods, you have a pair of curly braces. All the methods defined within these braces belong to this class. They live inside it.
Okay, so if a function lives inside a class, we specifically call it a method. Is that distinction really important in Java?
It is, yeah. It's an important distinction. In Java, once a function is defined within a class, it's accurately called a method. It's not just, semantics. It reflects Java's object-oriented nature.
Yes.
Well, methods are inherently tied to classes, representing behavior that objects of that class can perform. This contrasts with languages like Python, where functions can exist independently outside of any class structure. In Java, methods live in classes.
And often we see keywords like public or maybe private before classes and methods. These are access modifiers, right? What's their job?
Access modifiers are crucial for controlling visibility. They're special keywords, public, private, protected, or the default one, which is package private, that determine if other classes and methods can access these classes and methods.
So like permissions.
Kind of, yeah. Public is the most common and least restrictive one you'll see initially, especially for your main classes and the main method. It basically means that class or method can be accessed from anywhere in your program. Understanding these helps you control what parts of your code are exposed versus what parts are internal details.
Okay, so we've got classes and methods, and they need names. Are there specific naming conventions Java developers stick to? Because consistency is always a big deal for readability.
Oh, absolutely paramount. Consistency in naming is huge, especially when you're working in a team or just looking back at your own code months later. In Java, there are two main conventions to follow strictly. For classes, we use Pascal naming convention.
Pascal case.
Right. That means the first letter of every single word should be uppercase, no spaces. So, main class, mortgage calculator, my first program.
Got it. And what about for methods and variables? Same thing.
Nope, different convention there. For methods and variables, Java uses the camel naming convention.
Camel case.
Exactly. With camel case, the first letter of every word should be uppercase except the very first word. So you'll see names like main method, send email, or calculate mortgage. And for variables, my variable, username, total amount.
Ah, so that clearly distinguishes the main class from the main method inside it.
Precisely. Following these conventions isn't just style. It makes your code instantly recognizable, predictable, and much, much more readable to any Java developer.
We've talked about classes organizing methods, but what happens when you have like hundreds or even thousands of classes in a big application? You don't just dump them all in one place, surely.
Definitely not. That would be chaos, impossible to manage or find anything. That's exactly why Java has packages.
Packages, okay, like folders?
Pretty much, yeah.
Yeah.
Packages are designed to logically group related classes, just like folders organize files on your computer. This is absolutely crucial for managing large-scale applications that might contain, as you said, hundreds or even thousands of classes.
So packages are like super folders for classes, another layer of organization. And is there a specific naming convention for packages too?
Yes, and it's a very strong convention you'll see everywhere in professional Java. The base package name is typically the domain name of your company in reverse.
Domain name in reverse, how does that work?
So if a company's website is codewithmosh.com, their base Java package would be com.codewithmosh.
Ah, I see. .com.codewithmosh.
Exactly. This isn't just arbitrary. It creates a unique namespace for our classes. This is incredibly important for preventing naming conflicts. Imagine you're using two different libraries and both happen to have a class named Logger.
Right. How would Java know which one you mean?
Without packages, it wouldn't. The package provides that unique identifier. So com.mylibrary.logger is clearly distinct from org.anotherlibrary.logger. Problem solved.
So we've covered a lot of structure, methods and classes and packages, specific naming rules. Why is understanding all this organization so important for someone just starting out? It feels like a lot up front.
Well, understanding these structural elements isn't just about learning syntax rules. It's about learning the fundamental logical framework for building robust, scalable, and importantly, organized Java applications.
Building good habits early.
Exactly. It instills good habits from day one. Without this foundation, even simple programs can quickly become tangled messes, hard to debug, impossible to maintain as they grow. It's the blueprint for well-engineered software, ensuring your code is functional, understandable, and adaptable long-term. It's about building software that lasts.
All right, we've walked through the theory, set up our environment meticulously. Now, the moment of truth, creating our very first Java program. We're tackling the classic hello world. How do we kick this off inside IntelliJ IDEA, our chosen workbench?
Okay, the process in IntelliJ is nicely streamlined. You start by opening IntelliJ and choosing Create a New Project.
Create new project, okay.
In the wizard that pops up, on the left, you select Java as the project type. And critically, you make sure the Java development kit, the JDK you installed earlier, maybe version 12 like Mosh used, is correctly selected as the project SDK.
Right, telling IntelliJ which Java version to use.
Precisely. It needs to know which compiler and runtime to use.
And then we choose a template, right? What kind of application are we building first?
Right. For mastering the core Java fundamentals, Mosh strongly advises choosing the Create Project from Template option and specifically selecting Command Line Application.
Command line, no fancy graphics yet?
Not yet. This type runs purely in the terminal or console. While GUIs are exciting, starting with Command Line apps lets you focus purely on the core Java logic, syntax, and execution flow without getting tangled in visual design complexities early on. Then you just give your project a name, like Hello World.
And that base package idea we just discussed, does that come into play right away?
It absolutely does. Reinforces its importance right from the start. You'll set up your base package right there in the project creation wizard, following that reverse domain convention like com.codewithmosh or whatever yours is. This immediately establishes the namespace, even for a simple Hello World.
So, project created, IntelliJ shows us a file and folder structure. How do we navigate that? Where's the main.java file it generates?
Okay, on the left side of IntelliJ, you'll see the project panel. That's your navigator. Your main source code is usually inside a SRC folder, short for source.
SRC.
Inside SRC, you'll see your package structure like com.codewithmosh, and finally, inside that package, you'll find your main.java file. And remember, all Java source code files, by strict convention, must end with the .java extension.
And what's that package statement usually right at the very top of the main.java file?
Yes. At the very top, you'll see a package statement. This line explicitly declares which package the class defined in that file belongs to, its formal organizational address. And just a reminder, as a consistent rule in Java, wherever we have a statement, we should terminate that statement with a semicolon.
Semicolon. Got it. Like
Yep.
C# or C++ bed. Easy to forget.
Very easy. The compiler will definitely let you know if you do.
Okay, let's zoom in on that default main.java file IntelliJ gives us. What's actually inside that public class main block, and more importantly, that public static void main string args method? Can you break down that syntax?
Let's break it down. First, public class main. Public is the access modifier, meaning the class is accessible from anywhere. Class is the keyword defining a class, and main is its name, following Pascal case. Now, inside that class, the big one, public static void main string args. This is the main method signature, absolutely crucial.
Okay.
Again, access modifier. The Java system needs to be able to call this from outside. Static. This is important. We'll dive deep into static later. But for main, it means the Java system can call this method directly without needing to create an object of your main class first. It's the starting line, ready to go.
Makes sense.
The return type, main, doesn't return any value when it finishes. Main. The specific name Java looks for is the program's entry point. Has to be main. String args. This is a parameter. It's an array of string objects. It allows you to pass values into your program when you run it from the command line, maybe configuration details or something. We'll explore using these later, but for Hello World, we ignore them.
Okay.
And remember the convention? The left curly brace for the method body usually starts on the same line.
And what about those lines starting with may? Comments.
Exactly.
Yeah.
Comments.
Yeah.
Mosh reminds us they're purely for humans. They don't get executed by the compiler. They're completely ignored. Their only job is to explain our code to other people. Future you, colleagues, whoever. Good comments are invaluable.
Right. Okay, moment of truth. The iconic hello world. How do we write that line inside main, and what does system.out.println hello world actually mean piece by piece?
Okay, the classic line. System.out.println hello world. Let's dissect it. System. This is a fundamental class in Java, part of the java.lang package. This package is so essential, Java imports it automatically. You never need an import statement for it. IntelliJ often shows a little icon next to system indicating it's a class.
Ah, okay.
This is a special field. Think of it like a public variable inside the system class.
Yeah.
Its type is printstream, which is another class specifically designed for handling output, like sending text to your console.
Printstream, okay.
Println. This is a method belonging to that printstream class. The ln stands for line, so it literally means print line. Whatever you put inside its parentheses gets displayed on your terminal, and crucially, it adds a new line character at the end.
So the next output starts on a new line.
Exactly. Hello world. This is the actual data we want to print. It's textual data, specifically a string. In Java, a string is a sequence of characters and must always be enclosed in double quotes.
Double quotes for strings. Got it.
And a little pro tip Mosh mentions, in IntelliJ you can just type sout and hit tab, and boom, it expands to system.out.println for you.
Oh, nice shortcut. Sout plus tab.
Super handy. Once you've typed the line, running it is usually just a keyboard shortcut, like Threshold plus R on Mac or Shift plus F10 on Windows. And you'll see Hello World pop up in the terminal window at the bottom of IntelliJ. That moment, seeing your code actually run, it's pretty satisfying.
That is the magic moment. But what's really going on under the hood when we hit that run button? How does our English-like Java code turn into something the computer actually executes?
This is where you get that aha moment about Java's power. There are two core distinct steps involved: compilation and execution.
Compilation and execution.
Let's start with compilation. When you hit run, IntelliJ uses the Java compiler part of the JDK you installed. The compiler's job is to take your human-readable Java source code, those .java files,
Our main.java.
right, and translate it into an intermediate format called Java bytecode. This bytecode isn't directly runnable by your computer's processor yet.
So Java files become bytecode. Where does this bytecode live? Is it a file?
Yes, it's stored in files with a .class extension. So your main.java becomes main.class. Mosh even shows you can do this manually in the terminal with the javac command, like javac main.java. These .class files usually get placed in your project's out folder, maybe somewhere like outproduction hello world com, code with mosh main.class. Now, the absolutely crucial feature of this Java bytecode is its platform independence. This is key. It means this .class file can run on Windows, Mac, Linux, or any operating system that has a Java runtime environment. It's like a universal language for Java machines.
Universal, platform independent. That brings us to the second step, execution. What role does the JRE play? How does Java achieve that famous write once, run anywhere?
Right. The Java Runtime Environment, JRE, is the star here. Remember we said the JDK includes the JRE?
Yeah.
Well, the JRE includes a vital component called the Java Virtual Machine, JVM. The JVM's job is to take that platform-independent Java bytecode, your .class files, and translate it on the fly into the native machine code for whatever operating system you're currently running on.
Ah, so the JVM is the final translator for the specific OS.
Exactly. If you're on Windows, the JVM turns the bytecode into Windows instructions. On a Mac, it turns it into Mac instructions. It is. This architecture is precisely the reason why Java applications are portable or platform independent. You can write a Java program on a Windows machine, compile it to bytecode, take that exact same bytecode style, and run it on Linux, Mac, or any other OS that has a JRE installed. The JVM bridges the gap.
And Mosh mentioned other languages do something similar.
Yeah, he notes that C# with its runtime and Python with its interpreter share similar concepts of platform-independent execution. But the specifics differ. It's a common approach for portability.
So IntelliJ really smooths this whole process over for us, doesn't it? Compilation, then execution.
It absolutely does. IntelliJ skillfully hides these separate steps. When you click Run, it seamlessly handles compiling your .java class bytecode and then executing that bytecode using the JVM. It's all one integrated workflow, letting you focus on writing code, not managing the build process.
This whole under-the-hood flow source to bytecode to machine code via the JVM feels really fundamental. Why is understanding this important for a learner beyond just being interesting?
Well, it gives you that crucial aha moment for how Java actually delivers on write once, run anywhere. It makes that promise concrete. But more practically, knowing this helps you understand why certain errors happen at compile time versus runtime. It gives you a deeper conceptual model that's incredibly empowering for debugging.
Right, it helps you figure out where things went wrong.
Exactly. You can anticipate behavior better across systems, and you move beyond just knowing what to type to truly understanding how Java works. It makes you a better problem solver, not just a code typer.
Okay, so environment setup, check. First program running, check. Execution process understood, check.
Now let's dive into core concepts for building more dynamic stuff. We need to store data, right? That brings us to variables and constants. What are variables for in Java?
Variables are essentially named containers in your computer's memory. They're used to temporarily store data that your program needs to work with.
Temporary storage. Yeah, information your program will use, maybe change or display while it's running. Think of them like labels on boxes in a warehouse. Each box holds something specific you can access or change later.
How do we actually declare one and give it a starting value in the code?
It's a straightforward syntax. First, you specify the data type, what kind of info it holds, like a whole number int. Then its name or identifier, something meaningful. Then the assignment operator, the equal sign. And finally, the initial value. So IntelliJ declares an integer variable called age and gives it the starting value 30.
In age, each is 30. Type, name, assignment, value.
Exactly. And the key thing about variables is they're mutable. Their values can be changed later. You could write age yellow star 35 on the next line, and the value stored in age updates. Mosh really stresses using meaningful names like my age or views count and sticking to that camel case convention for readability.
So variables can change, but what if you have data that shouldn't change, like, say, the value of pi? That's where constants come in.
Precisely. Constants are for values that we don't want to change once they're set. Pi is a perfect example. To declare a constant in the Java, you use the final keyword right before the type.
Okay.
So final float pi equals 3.14f. That final keyword makes the value immutable. Once initialized, if you try to change it later, like pi equals 3.14159, the Java compiler will give you an error. It stops you from accidentally changing fixed values.
Which is good for preventing bugs. And constants have their own naming style too, right? Not camel case.
Right, another important convention for readability. For constants, the standard is all capital letters, using underscores to separate words.
Oh, okay. Like months and year.
Exactly, or max connections. Mosh even shares a funny story about mispronouncing pi as p in an early course, a memorable reminder of why these explicit conventions help.
So data itself comes in different flavors: whole numbers, decimals, single letters, true, false. Java needs to categorize these, which is where data types are fundamental. Mosh breaks them into primitive types and reference types. Let's start with the primitive types. What are they, generally?
Primitive types are the most basic fundamental data types in Java.
Sure.
They're used for storing simple values directly in memory. They're highly optimized and represent single atomic pieces of data.
Okay, like the building blocks. What are the main ones for numbers?
For whole numbers, Java gives you options based on the size of the number you need to store and how much memory you want to use. Byte. Smallest, just 1 byte. Stores -128 to 127. Good for things like age, maybe.
Yeah.
Short. 2 bytes up to about 32,000. Int, the most common one. 4 bytes up to around 2 billion. Your default choice for integers, usually. Long. For really big whole numbers, 8 bytes. If you write a large number literal, you need an L at the end, like 300,000,000,000,000L.
And you mentioned underscores for readability.
Yeah, great trick, Mosh points out. 1, 2, 3, 4, 5, 6, 7, 8, 9, 0. Java ignores the underscores, but it makes huge numbers way easier for humans to read.
Nice tip. What about numbers with decimal points?
For decimal numbers, you have float, 4 bytes. If you write a literal float, you need an F at the end, like 1099F. Double,
Yeah.
8 bytes. This is the default for decimal literals if you don't specify F. More precise generally.
Okay. And single characters, like A or...
For single characters, use char. It takes 2 bytes and stores 1 character. Importantly, characters are always in single quotes, like A or %. And char can handle international letters too, not just basic English ones.
Single quotes for char, double quotes for string. Got it. And the last primitive.
The last one is for Boolean values. Boolean. This just stores true or false. Absolutely fundamental for making decisions in your code.
True or false. Simple. And you mentioned reserved keywords.
Right. Words like public, static, void, class, package, and all these primitive type names in byte, float, Boolean, etc. are reserved keywords. You absolutely cannot use them as names for your variables, classes, or methods. They have special meanings to Java.
Okay, those are the simple primitive types. Now, what about reference types? What's the core idea there, and how do they differ in what they store and how they're managed? This feels important.
It is very important. Reference types are used for storing complex objects. Think of things like a date object holding a specific time, or a mail message object, or maybe a custom user object you define yourself with, name, email, ID, etc.
So anything that's not one of those 8 primitives.
Basically, yes. If it's not a primitive, it's a reference type. The key difference in how you declare them often involves the new operator. You use new to allocate memory on a special area called the heap for this new complex object. For example, date now week's new date. Creates a brand new date object in memory, and the now variable holds a reference like an address pointing to where that object lives.
A reference, not the object itself directly in the variable.
Exactly. That's the crucial difference from primitives, where the value is stored directly in the variable's memory spot.
So if new allocates memory, does that mean we have to manually clean up that memory later, like in some older languages?
Thankfully, no. That's a huge advantage of Java. The Java Runtime Environment, JRE, has something called a garbage collector. It's this automatic process that keeps track of objects in memory. When an object is no longer referenced or needed by your program, the garbage collector automatically reclaims that memory.
Automatic memory management. That sounds like a relief.
It's a massive relief. It prevents a whole class of nasty bugs like memory leaks that you have to constantly worry about in languages with manual memory management. And just to be precise, an object like our now variable is called an instance of a class. The class, date in this case, is the defined template or blueprint. The object now is an actual thing created from that blueprint. Like John might be an instance of a human class.
Blueprint versus actual instance.
Yeah.
Got it. And once we have one of these complex objects, how do we interact with it? Access its data or make it do things?
That's where the dot operator comes in. You use the dot operator to access the members of an object. Members can be methods, actions the object can perform, like now.getTime to get the time, or fields, data stored within the object.
So object.memberName.
Exactly. Primitive types, remember, don't have members you can access with a dot because they're just simple values, not complex objects with internal parts. And one more vital thing. When you use a class from a different package than your current file, you usually need an import statement at the top, like import java.util.date. This tells Java exactly where to find the date class blueprint. It avoids confusion if multiple packages happen to define a class with the same name.
The import statement clarifies which date class we mean. Okay. This primitive versus reference type distinction feels really fundamental, especially when Mosh talks about memory management. Can you elaborate on that crucial difference? It seems like a place where subtle bugs could creep in.
Oh, absolutely. This distinction isn't just academic theory. It's the source of countless subtle, maddening bugs if you don't grasp it properly. It's fundamental for understanding how data behaves. Okay, so when you assign primitive types, they are copied by value. What does that mean? If you have int x, x, and then int y, y, x, Java makes two completely independent variables.
Two separate boxes.
Exactly. X and Y each hold their own copy of the value 1 at different memory locations. So if you then change X later, like X is 2, Y doesn't care. Y still holds 1 because it got its own separate copy initially.
Makes sense. Primitives are separate copies. What about reference types then? This is where it gets tricky.
This is exactly where the common pitfalls lie. Reference types are copied by reference. So if you create an object, say point P1 equals new point 11, using the point class, for example, and then you write point P2 equals P1, you do not get two separate point objects.
No. What happens then?
Instead, both P1 and P2 are referencing the exact same point object in memory. They don't store the object's data directly. They store the address or the reference to that single point object living on the heap.
So they both point to the same thing?
Exactly. And the consequence is huge. If you modify the object using either variable, say p1.x equals 2, that change will be visible to the other variable. If you then check p2.x, it will also be 2, because they're both just different labels pointing to the same underlying data. Mosh uses the java.outPoint class to really demonstrate this clearly.
Wow, okay. That sounds like a major gotcha for beginners.
Right.
Why is understanding this memory difference, copy by value versus copy by reference, so critical for avoiding those subtle bugs?
Because if you don't understand this, you'll inevitably make a change through one variable and be mystified when some other, seemingly unrelated part of your code suddenly behaves differently. It leads to hours of frustrating debugging.
I can imagine.
Understanding this distinction lets you predict how data will behave when you pass it around in your program. You know when you're working with a copy and when you're working with a shared reference. It clarifies how data is truly shared and manipulated, making you a much more effective debugger and helping you write more robust, predictable code. It's the difference between guessing and knowing.
Okay, let's talk about text. It's everywhere in programming, usernames, messages, web content. How does Java handle this vital data type? What's special about strings?
Strings are indeed ubiquitous in Java and have some unique traits. While they are technically a reference type, they represent objects. Java gives us a special convenience. You can initialize string variables using a literal directly, just like primitives.
Oh, so you don't always need the new keyword for strings.
Exactly. You can just write string message hello world without needing new string. Hello world. This shorthand makes working with strings feel very natural.
And Mosh introduces a really important concept about strings, immutability. What does that mean for how we use them?
Immutability is a cornerstone concept for Java strings. In Java, strings are immutable. This means once a string object is created, its actual sequence of characters cannot be changed. It's fixed.
But wait, what about methods like replace or to lowercase? Don't they change the string?
Great question. This is where the immutability concept is key. Any method that seems to modify a string, like message.replace, actually returns a new string object containing the modifications. It doesn't alter the original message string in memory at all.
So it creates a brand new string with the changes.
Exactly. Your original message variable still points to the original unchanged hello world string. If you want to use the modified version, you have to capture the result of the method call, maybe by assigning it back to the variable like message.replace or assigning it to a new variable.
Okay, that's a crucial detail. So if they're immutable, how do we do common things like joining strings, checking their length, or changing case?
The string class provides a rich set of useful methods, all accessed using the dot operator. For joining strings, the plus operator is super convenient. Hello plus world. Other common methods include .ends with and starts with. To check if a string begins or ends with certain characters, returns the number of characters. Really useful for input validation, like checking password length, index of. Finds the first position, index of a character or substring, or returns -1 if it's not found, replace. As we said, returns a new string with replacements made to lowercase and to uppercase. Also return new strings, converted to the specified case. Trim, super useful for user input. Returns a new string with leading and trailing white space removed. Cleans things up nicely.
Trim sounds very handy. Mosh also clarifies parameters versus arguments when talking about methods. Can you quickly explain that distinction? People often mix them up.
Yeah, it's a good distinction to nail down. Parameters are the variables listed in the method's definition, the placeholders for the values the method expects. In void print message, string text is the parameter.
It's a placeholder in the definition.
Right. Arguments are the actual values you pass into the method when you call it. So if you call print message hi there, the string hi there is the argument being passed to the text parameter.
Parameter is the slot, argument is the value that fills it. Got it. And sometimes with strings, we need to include special characters, like quotes inside quotes or backslashes for file paths. How does Java handle that without getting confused?
That's where escape sequences come in. There are special combinations, starting with a backslash, that tell the Java compiler to treat the next character literally, not as code syntax.
Ah, like tells Java don't treat the next character specially.
Exactly. They're essential for representing characters that have special meaning in strings. For instance, lets you put a double quote inside a double quoted string, like system.out.println. She said, hi. Lets you include a literal backslash, crucial for Windows file paths like C. It lets you include a literal backslash, crucial for Windows file paths like C, and creates a new line. Lets you include a literal backslash, crucial for Windows file paths like C. T creates a tab space. Lets you include a literal backslash, crucial for Windows file paths like C. These sequences prevent errors and ensure your string actually contains the characters you intend.
Okay, we've covered individual data pieces in text, but often we need to store collections of items like a list of scores or a group of names. That's where arrays come in, right? What's their main purpose and how do we declare them?
Yes, arrays are fundamental for storing collections. They're designed to store a list of items where all items are of the same type. You can have an array of ints, an array of strings, but not a mix in the same array. To declare one, you specify the type, add square brackets, +, give it a name, then use new, the type again, and the size in brackets. For example, int numbers equals new int type 5. Declares an array named numbers that can hold exactly 5 integers.
Size 5. And what's a crucial characteristic or maybe limitation of arrays that Mosh highlights? Seems important for beginners.
A crucial limitation. In Java, arrays have a fixed size. This is non-negotiable. Once we create them, we cannot add or remove additional items. The length is set when you create it and can't change dynamically. If you need more space later, you have to create a whole new, bigger array and copy everything over.
Fixed size. That's important. How do you access the items inside?
You use zero-based indexing. The first item is at index 0, the second at index 1, and so on. So for our size 5 array numbers, the valid indices are 0, 1, 2, 3, and 4. Number 0 gets the first element. Numbers 4 gets the last. Trying to access numbers 5 would cause an error, an array index out of bounds exception, and crash your program. Very common beginner mistake.
What if I declare an array like new int 5 but don't put anything in it immediately? Are the slots empty?
No. Java initializes them with default values based on the type. For an int array, they all start as 0. For Boolean, they start as false. For string arrays, or any other reference type array, they start as null.
Null, okay. And you can't just print the array variable directly, right?
Right. If you do system.out.println numbers, according to make numbers, you get a weird string representing its memory address. To see the contents nicely, you need a helper method, arrays.toString. You'd write system.out.toString. That comes from the java.util.arrays class, so you'll need an import, java.util.arrays statement.
Arrays.toString. Good to remember. Is there a shorter way to create an array if I already know the values I want in it? Like 1, 2, 3.
Absolutely. Much more convenient. If you know the values up front, you can use curly braces for direct initialization. Int numbers 2, 3, 5, 1, 4. Java figures out the size automatically, size 5 in this case. It's much cleaner than new NP5 followed by 5 assignment lines.
Nice. And how do you find out how long an array is?
You use its length field. Not a method, just a field. Numbers.length, that would give you 5 for our example.
Numbers.length, okay. Can you sort arrays easily?
Yep. The same arrays class has a sort method, arrays.sort numbers. It sorts the array elements in place, usually in ascending order.
What if my data isn't just a list, but more like a grid or a table, rows and columns? Can arrays handle that?
Yes, Java supports multi-dimensional arrays. Perfect for grids, matrices, game boards, etc. For a 2D array, like a matrix with 2 rows and 3 columns, use double square brackets. Int matrix, new int T23.
Double brackets, okay.
Accessing elements requires 2 indices, matrix row column. So matrix 100 is the top left element. To print these nicely, you can't use arrays.toString. You need arrays.deepToString matrix, which handles the nested structure. And yes, you can also use nested curly braces for shorthand initialization if you know all the values, like int matrix, yeah, is 1, 2, 3, 4, 5, 6.
Okay, arrays covered. Now, we often need to convert data between types, right? Like an int to a double or maybe the other way around. That's casting and type conversion.
Precisely. Java is strict about types, so sometimes you need to explicitly convert. There are 2 main ways, implicit and explicit casting.
Implicit first. Sounds automatic.
Yeah, implicit casting or automatic conversion happens when there's no chance for data loss. Java does it for you behind the scenes. For example, assigning a short to an int is fine because an int can hold any short value. The short is implicitly widened to an int. The general widening hierarchy is byte short int long and also float double. You can also implicitly cast an int to a double, like in 10 3.0, the 10 becomes 10.0 for the calculation.
So it happens automatically when going from a smaller type to a larger one where no info is lost. When do we have to step in and do it manually? That must be explicit casting.
Correct. Explicit casting is needed when data loss is possible, or you specifically want to narrow a value to a smaller type. You have to tell Java you know what you're doing by putting the target type in parentheses before the value. For example, casting a double to an int or y, int or 1.1 plus 2. The result is 3. The 0.1 decimal part is simply chopped off, lost, because ints can't store decimals.
So int forces the conversion, even with data loss.
Exactly. You're telling the compiler, I accept the potential data loss. Mosh stresses, though, that explicit casting only works between compatible types. You can cast numbers to other numbers, but you can't just cast a string like hello to an int using int. That requires different methods.
Ah, okay. So what if you do have a string, maybe from user input like 123, and you need it as an actual number for math? How do you convert that?
That's a super common scenario. User input is almost always text initially. To convert numeric strings into actual number types, you use special methods from Java's wrapper classes. These are object versions of the primitives. You'll use static methods like integer.parseInt123 returns the int123, short.parse short50 returns the short50, float.parseFloat 3.14 returns the float 3.14, double.parse double 99.9 and returns the double 99.9.
Integer.parseInt, float.parseFloat, etc. Got it. What happens if the string isn't a valid number? Like if the user types hello?
Ah, good question. If you try to parse something that can't be converted, like hello for parseInt, or maybe 1.1 for parse, which expects a whole number, your program will throw an exception, basically a runtime error, and likely crash. That's why checking input before trying to parse it is so important. We'll touch on that with error handling later.
Okay. Beyond basic math, we often need things like rounding, powers, maybe random numbers. Does Java have built-in tools for that, like a math library?
It absolutely does. Java provides the very useful math class. It's part of the core java.lang package, so you don't even need to import it. It's always available.
Nice. What can it do?
It has lots of static methods for common operations. Math.round rounds a float or double to the nearest whole member, returns int or long. Math.round 1.6f gives 2. Math.ceil, ceiling, gives the smallest whole number greater than or equal to the input. Math.ceil 1.1 gives 2.0. Returns a double, so you might need to cast it to int.
Ceiling goes up.
Right. And math.floor goes down. It gives the largest whole number less than or equal to the input. Math.floor 1.9 gives 1.0, also returns a double. Math.max AB and math.min AB. Return the larger or smaller of two values. Works for different number types. Math.pow, base exponent. Calculates base raised to the power of exponent. Math.pow23 is 8 over. Crucial for formulas like the mortgage one.
Pow for power is very useful. What about random numbers?
Math.random gives you a double value between 0.0 inclusive and 1.0 exclusive.
Just between 0 and 1, how do you get, say, a random number between 1 and 100?
You scale it. Multiply the result. Math.random. 100 gives a double between 0.0 and 99.999. To get a whole number, like 0 to 99, you cast it to int. But Mosh warns about order of operations here. You must cast the result of the multiplication. Int, math.random 100. If you do int math.random 100, you'll almost always get 0 because int math.random becomes 0 first.
Cast the whole thing. Good tip. Okay, numbers are great for math, but sometimes we need to show them to users nicely formatted, like with currency symbols, commas, or percent signs. Does Java help with number formatting?
Yes, and it's quite powerful, especially for different regions and languages. Java provides the number format class. It's in the java.text package, so you need an import java.text.number format.
Number format, yeah.
Now, this class is a bit special. It's abstract. You can't just create one directly using new number format.
Abstract's no new. How do you get one, then?
You use factory methods. These are static methods on the number format class itself that create and return a ready-to-use formatter object for you.
Like a factory producing the object.
Exactly. You use methods like numberFormat.getCurrencyInstance to get a formatter for currency. It automatically uses your system's default currency settings, like or euro, or numberFormat.getPercentInstance for percentages. Once you have the formatter object you call format method, passing in your number like a double or long, it returns a nicely formatted string.
So formatter.format, my number, gives back the string.
Precisely, like $1,234.76 or 75%. Mosh also shows method chaining, where you can do it all in one line, which is quite neat. String formatted, number format dot get currency instance dot format value. Very concise.
Method chaining.
Yeah.
Cool. Okay, programs that just run silently aren't very engaging. We need them to interact, especially by reading user input. How do we let users type things into our Java programs?
This is critical for making programs dynamic. To read user input from the console or terminal, Java provides the scanner class. It's in java.util, so you need import java.util scanner.
Scanner. Okay, how do you set it up?
You create a scanner object, telling it to read from the standard input stream, which is usually the keyboard. System.in, so scanner, new scanner system.in. Now scanner's ready to listen for input.
What kind of input can scanner read? Just text?
It's pretty versatile. It has methods to read specific types, trying to parse them automatically. Next byte, next float, next double. These try to read and return the corresponding primitive numeric type. Next reads just the next token or word, stopping at the first space or new line. The next line. This one is important. It reads the entire line of input, including spaces, up until the user hits enter. Often what you want for names or sentences.
Next for one word, next line for the whole line. Good distinction.
Yeah. Mosh gives a nice UI tip. Use system.out.print for your prompts, like enter your age, not print. Keeps the cursor on the same line, making it look cleaner when the user types their answer right after the prompt.
Print for prompts, println for output lines. Makes sense.
Also, Java handles concatenating numbers with strings nicely. If age is 30, system.out.println you are aired plus age. Just works. It converts age to a string automatically. Remember that trim method for strings. Mosh shows using it right after next line, like string name scanner.nextline.trim. To remove any accidental leading trailing spaces the user might type, makes the input cleaner, output more beautiful, as he says.
Trim after next line is a good habit. What if the user types something unexpected, like text when you use nextInt?
Yeah. That's the risk. If the input doesn't match the expected type, like ABC for nextInt, the program will throw an input mismatch exception at runtime and crash. This highlights why robust error handling and validating input are crucial for real-world apps.
Definitely. So user input really is the bridge to making programs interactive. Why is mastering this so vital for learners?
Because it's how your program stops being just a static script and becomes interactive. Without input, programs can only work with predefined data. Learning to read input safely and effectively lets you build responsive, adaptable applications that react to users, ask questions, get choices. It's what makes software truly useful to people.
Now we move into the really exciting part, control flow. This is where programs start making decisions, adapting, and repeating actions. Let's start with the basics of decisions, comparison operators. What are they for and what do they give back?
Comparison operators are fundamental. They're used to compare primitive values, mostly numbers, to see how they relate. The crucial output is always a Boolean value, either true or false. This true-false result is called a Boolean expression or condition.
Okay, true or false? What are the main operators we use?
The main ones are equality, double equals. Super important not to mix this up with which is assignment. Ask, are these equal? Inequality asks, are these not equal? Greater than, less than, greater than or equal to, less than or equal to, less than or equal to. These are the tools you use to build the conditions your program will check.
So we can compare two things, but what if we need to check multiple conditions at once? Like, is the temperature both above 20 and below 30? That's where logical operators come in.
Exactly. Logical operators let you combine multiple Boolean expressions to build more complex rules. Java has three main ones. First, logical AND, which is NAM. This requires both conditions it connects to be true for the whole thing to be true. If even one side is false, the whole NN expression is false. Mosh points out short-circuiting here. If the first part of NNN is false, Java doesn't even bother checking the second part because the result must be false anyway.
Saves a bit of work.
Yeah, an example is temperature 20 and temperature 30. Okay.
What about logical OR?
Logical OR is 8. This only requires at least one of the conditions to be true for the whole expression to be true. It's more lenient. It also short-circuits. If the first part of the AND is true, Java skips the rest because the result is already guaranteed to be true. Example, had high income, has good credit.
Either one is good enough. And the last one, negation.
Right, logical not, which is just, it reverses a value. If something is true, Jockey makes it false, and vice versa. So his criminal record would be true if the person does not have a record. Mosh shows how these are very useful in implementing real-world rules with multiple factors, like loan eligibility.
Okay, armed with comparisons and logical operators, we can finally make decisions. If statements are the workhorse here, right? What's the basic structure in Java?
If statements are absolutely the backbone, they let you run different code blocks based on whether a condition is true or false. The basic structure is if condition, code if true. You can add else if another condition, code for another possibility, and finish with an optional else, code if nothing above was true as a fallback.
And the curly braces for the code blocks. Always needed.
Technically optional if there's only one statement right after the if or else. But Mosh strongly advises always using them. You must use them if you have multiple statements for a condition. Even for one statement, using braces makes the scope clear, improves readability, and prevents bugs if you later add more code without remembering the braces. Just always use them.
Good advice. Always use braces. Mosh also mentions simplifying else-if conditions.
Yeah, often you can remove redundant checks. If you already checked if temp30, then the next else if temp20, you don't need to also check temp30 because that's already implied by the fact you reached the else if. The second condition just needs to be temp20.
Ah, makes the logic cleaner. And he showed a neat way to refactor simple if-else blocks for assigning Booleans, making it more professional.
Absolutely.
Yeah.
He starts with an amateurish way, maybe declaring a Boolean inside the if and else, which can cause scope errors. Then an improved way, declare the Boolean outside, initialize to false, set to true, inside the if.
But the best way.
The most professional way for simple Boolean assignments is to assign the result of the condition directly to the variable. Instead of an if-else, just write Boolean has our income equal 100,000. The comparison, income 100,000, already produces true or false, so you just assign that result directly. He suggests using parentheses around the condition for clarity, even if not strictly needed. It's concise and very readable.
Boolean, variable, condition, very clean. Okay, related to if, Mosh mentioned a very cool technique for simplifying just these kinds of assignments, the ternary operator. How does that work?
The ternary operator is like a super compact if-else statement, specifically for assigning a value based on a condition, all on one line. The syntax is condition value if true, value false.
Question mark and colon.
Right. So instead of a full if-else to set a class name based on income, you can write string class name income 100,000. First, economy. If the condition income 100,000 is true, class name gets first, otherwise it gets economy. Mosh calls it the simplest, most elegant, and the most professional way for these specific scenarios. Makes code very concise.
Neat. What if you have, many possible specific values for something and want different actions for each? Is there an alternative to a long if-else if f.chain?
Yes, that's exactly what switch statements are good for. They let you execute different parts of code depending on the value of an expression. Often cleaner than a long if-else if chain when you're checking against a set of discrete values. The syntax looks like this. Java.switch, variable to check, case value 1, case of value 1 to value case value 1 dot fill for value 1 and case value 1 dot case value 2 dot break, case value 2 dot break, default optional code if no case matches default.
That break statement inside each case seems important. What happens if you forget it?
Oh, break is absolutely critical. It means jump out of this switch block once a matching case is found and executed. If you forget break, execution falls through to the code in the next case block and the one after that till it hits a break or the end of the switch. This fall through is almost never what you want and is a classic source of bugs.
So always put a break in each case. Got it. What about default?
Default is optional. Its code runs if the variable to check doesn't match any of the specific case values. It's like the final else in an if-else if chain. Switch statements work well with strings, ints, bytes, shorts, chars, and enums, but not directly with longs or float doubles.
Okay. Mosh uses a popular interview question, FizzBuzz, to illustrate conditional logic. Can you explain the problem and the common mistake people make?
FizzBuzz is a great little puzzle. The task is, take a number as input. If it's divisible by 5, print fizz. If it's divisible by 3, print buzz. If it's divisible by both 5 and 3, print FizzBuzz, otherwise print the number itself.
Sounds simple enough. What's the catch?
The catch is the order of the checks. Many beginners write their if-else if-is like this. Check for divisible by 5, print fizz, then check for divisible by 3, print buzz, then check for divisible by both, print FizzBuzz. The problem, if the input is 15, divisible by both, the first condition, divisible by 5, is true, so it prints fizz and stops. The FizzBuzz condition is never reached for 15.
Ah, the order matters. So what's the right way?
The right way, and Mosh's advice is, place the most specific conditions on the top and the most generic ones on the bottom. So, you must check for divisible by both 5 and 3, which means divisible by 15 first. If that's true, print fizzbuzz. Only then, in else if blocks, do you check for just divisible by 5, fizzbuzz, and then just divisible by 3, buzz. This ensures the most specific case, fizzbuzz, is caught before the more general ones.
Check the most specific case first. Makes sense. Mosh also mentioned trade-offs here.
Yeah, great point about real-world programming. He acknowledges the DRY principle, don't repeat yourselves. But he argues that for fizzbuzz, the flat structure of the corrected if-else-if chain, checking 15, then 5, then 3, is actually cleaner and easier to read than trying to use complex nested ifs just to avoid slightly repeating the divisibility checks. Sometimes clarity wins over absolute adherence to one principle. Programming involves trade-offs.
Good lesson. Okay, beyond decisions, programs need repetition. Processing lists, asking for input until it's right. That's loops, right?
Yep.
What's their general purpose? And let's start with for loops. When do we use those?
Exactly. Loops are for efficiently repeating one or more statements without copying and pasting code. Indispensable. For loops are your best choice when you know ahead of time how many times you want to execute something. Perfect for definite iteration. The syntax packs everything into one line for initialization, condition, increment, decrement.
Code to repeat.
In OS's condition increment, okay.
So to print hello 5 times.
Yeah.
For int, inu, i5, i++. IntelliJ $00 runs once at the start. I5 is checked before each loop. I++ runs after each loop body. Easy to implement for counting up, down, etc.
And while loops, when are they better and how do they differ?
While loops are better in situations where we don't know exactly how many times you want to repeat something, they run as long as the condition stays true. The classic example is asking for user input until they type quit.
Because you don't know how many tries it will take them. Exactly. The syntax separates the parts. Initialization, while condition, update that, affix condition. The key difference for Freyr is the condition is checked before the first iteration. If it's false initially, the loop body never runs. Mosh also gives a best practice for input loops. Create the scanner object outside the loop to avoid creating a new one every single time, which just pollutes memory.
Good tip, scanner outside the loop. And remember, equals for strings, not...
Yes. And use to lowercase on the input before comparing, like input.to_lowercase.equals quit to make it case insensitive. Much more user-friendly.
There's also a do-while loop, right? What's special about that one?
Yeah, the do-while loop. Less common, but has its place. Syntax is do code while condition. The key difference, the code block in the do part runs at least once before the condition is ever checked. Condition is evaluated at the end. Useful if you need to guarantee at least one execution, like prompting for input once before validating.
Okay. And loops can be controlled with break and continue.
Yep. Powerful control statements. Break. Immediately terminates a loop. Jumps to the code right after the loop, no matter what, like an emergency exit. Continue. Skips the rest of the current iteration and moves control to the beginning of a loop for the next iteration, if the condition still allows.
Yeah.
Like skipping one item on a list and going to the next.
Useful. Mosh warned about while true loops.
Yes, a common pattern is while true, to make an infinite loop on purpose, but then you must have an if condition inside that executes a break statement to eventually get out. Like if input.equals break. The warning is, if you forget the break or the condition is never met, you have a real infinite loop that never ends and will likely freeze your program. Use with care.
Use while true carefully with a guaranteed break. Got it. Lastly, for each loops. They look different. When are they useful?
The for each loop, or enhanced for loop, is specifically designed to iterate over arrays or collections, when you just need to process each item one by one from start to finish, and you don't need the item's index. It's position.
Simpler syntax for simple iteration.
Exactly. Syntax is super clean. For element type element dot array or collection, for example, for number not number, system.out.trindle in n and number. Mosh says it's much easier to iterate over an array this way for simple cases.
What are the limitations?
Key limitations. It's always forward only. You can't go backwards. And critically, here we don't have access to the index of each item. If you need the index for some reason or need to go backwards, you have to use a traditional for loop with an index variable for int I equals 0.
Okay, that covers loops. We've built up a lot of tools. Mosh brings it all together in a practical mortgage calculator project and then refines it with error handling. Can you recap the calculator's goal and input?
Right, the project goal.
Yeah.
Calculate monthly mortgage payments. A very real-world task. It needed 3 inputs from the user. 1, the principal, loan amount. 2, the annual interest rate. 3, the period, loan duration in years. He shows a standard formula, MPI 1 plus IN, 1 plus IN1. But reminds us of the key steps. Convert annual interest to monthly interest by dividing by 100, then 12. Convert years to total number of payments, n by multiplying by 12. And math.pow is needed for the 1 plus IM part.
Okay, so you build the basic calculator, and then Mosh immediately flags issues with error handling and input validation. What went wrong, and what was the fix?
The initial version was fragile. It crashed if the user typed text instead of numbers, or if they entered valid numbers that didn't make sense for a mortgage, like a negative principal, 0 interest, maybe 500 years.
Yeah, need to guard against that.
The solution strategy was using those infinite loops, while true, around each input prompt.
The while true loop again. How did the validation work inside it?
Okay, so inside the loop for, say, getting the principal. 1. Read the input, e.g. scanner.nextDouble. 2. Use an if statement to check if the value is in the valid range. Principal equals 1,000 and principal equals 100,000. 3. If it is valid, execute break. This exits the while true loop, and the program moves on to ask for the next input. 4. If it's invalid, the if condition is false. An else block runs, printing a clear error message, enter a value between 1,000 and a million billion. Since break wasn't hit, the while true loop repeats, prompting the user again for the same input.
So it keeps asking until it gets valid input. Very robust.
Exactly. Makes the program much more user-friendly and prevents crashes.
I remember a common snag here. Variable scope. Declaring variables inside the loop caused problems.
Yes, a classic. If you declare a principal inside the while true loop, it only exists inside that loop. When the loop finishes, after a break, the variable disappears, and you get a cannot resolve symbol error if you try to use principal later for the main calculation.
Ah, so how do you fix that? Simple fix. Declare the variables, in principal, float annual interest, by years, outside and before their respective while loops, usually at the top of the main method, maybe initializing them to 0. This gives them scope throughout the main method. Mosh also stressed calculating derived values, like monthly interest, inside the if block where input is confirmed valid right before the break. Don't calculate with potentially invalid data.
Declare outside, assign calculate inside the validation if.
Got it.
So this mortgage calculator project ties everything together nicely, but Mosh uses it to point towards the next challenge, code maintainability. What problem starts creeping into the main method, and what's the professional solution?
This is a key transition point. With all the input prompts and validation loops added, the main method starts getting really long, maybe hundreds of lines. While it works, Mosh correctly points out this hurts the maintainability of our program.
Hard to read, hard to change later. Exactly.
Yeah.
Imagine someone new looking at it, or even you coming back in 6 months. It's just a long, scrolling wall of code. Hard to follow the overall logic, hard to debug, hard to modify without breaking something. This monolithic structure becomes a problem.
So what's the next step, the more professional approach?
The next step, which Mosh sets up for future learning, is breaking this code down into smaller, easier to read, and easier to understand chunks. This means refactoring, extracting logical pieces of code into their own separate, well-named methods.
Ah, like creating a read principal method, maybe a calculate monthly payment method.
Precisely. Your main method then becomes much shorter, like an outline calling these other methods. It reads like a summary of steps. The individual methods are focused, easier to understand, test, and reuse.
And he reinforces this with a great quote.
He does. He quotes Martin Fowler, a well-known software expert. Any fool can write code that a computer can understand. Good programmers write code that humans can understand.
That's powerful. Hits the nail on the head.
It perfectly captures why structuring code for clarity, collaboration, and long-term maintenance is so vital. It's about software craftsmanship.
So recognizing when your code gets messy is a critical skill for a learner. What does it signal about their growth?
Absolutely. This project shows how complexity grows. Recognizing when code becomes unwieldy signals that shift from just making things work to making things maintainable and professional. This deep dive gave you the foundational building blocks. The mortgage calculator hints at the next level. Organizing those blocks effectively so your software scales, not just in features, but in human understanding.
And that brings us to the end of another deep dive. We've taken a really comprehensive journey into Java's core, haven't we? From setting up tools like the JDK and IntelliJ
to understanding the fundamental building blocks like classes and methods. And we pulled back the curtain on that crucial under-the-hood process compilation to bytecode, execution by the JVM.
Right. We explored how Java handles data with primitive and reference types, really digging into memory management differences.
We equipped ourselves with tools for math, formatting numbers, and crucially, making programs interactive by reading user input.
And finally, we dove into the programmer's brain. Control flow. Mastering decisions with comparisons, logical operators, if, switch.
And repeating actions efficiently with for, while, do while, and for each loops. All brought together in that mortgage calculator example, complete with error handling.
You've now genuinely gained a solid conceptual and practical foundation in Java programming. This isn't just theory, it's directly applicable knowledge for building real applications.
Absolute. The tools are there.
So as you start crafting your own Java programs armed with these powerful fundamentals, here's something to think about. What's the most complex real-world problem you could realistically start breaking down using just these building blocks, classes, methods, variables, control flow? How would you begin organizing its logic, ensuring it's not just functional, but also elegant, readable, and understandable to any human looking at it? The power to build, to solve, to create, it's really in your hands now.